Howdy everyone, my name is Abhishek Anchate and I'm a first year PhD student in the Department of Industrial and Systems Engineering here at Texas A&M. And today I'm going to present on the paper titled Implementing an Open Source Sensor Data Ingestion, Fusion and Analysis Capabilities for Smart Manufacturing. Beginning by going over the theme of the paper, in our work, we are working on enabling smartification of manufacturing firms via sensor integration, edge cloud computing, and developing an efficient communication architecture in order to implement a real-time open source data pipeline for process monitoring. Let us talk about the challenges to such an SM implementation, especially with respect to micro, small, and medium manufacturers. Over 90% of today's manufacturers are constitute of these MSMEs, and over 70% of the machines owned by these companies are legacy equipment. As we move towards more and more adaptation of smart manufacturing, the manufacturing environment is moving towards a paradigm shift of manufacturing as a service. And there has been a need of digitalization for these MSMEs to survive in this modern era. While technology for sensorization exists, such as retrofitting with commercial off-the-shelf sensors, such a sensorization scheme does not necessarily imply smartification. The data needs to be properly collected, stored, and preserved while maintaining its integrity. However, such a data processing pipeline is difficult. Complete package solutions do exist, but most of them are not affordable. For example, Holland Energy Park paid a whopping $120,000 to set up a Raspberry Pi solution at their park. Moreover, we are always going to run into the issues of competing proprietary protocols when we are trying to incorporate more than one of these solutions. All these points imbibe the need for an open source solution for such as effective smartification of machines. Moving on to the system architecture, our implementation consists of 5 layers. Firstly, there is the machine layer, which consists of the machines, the sensors, and the data acquisition systems, followed by which we have the edge adapters, which combine all the sensor data which is collected by the sensors and then preprocesses it before transmitting it further down the line. Followed by this, we have the data historian, which can be cloud or edge based depending on the requirements, and it is used to store and provide safety measures to the data, as well as it also keeps responding to the next layer, which is the analytics module. Coming to the analytics modules, the major purpose it plays here is to perform the desired analysis while also providing a user interface for the clients to play around with. The clients can specify certain parameters such as the sampling frequencies of the sensors in order to request the desired real-time analysis and visualization. Getting into more details of the smart manufacturing architecture itself, we have four major component blocks here: the machine, edge, middleware, and the cloud-based applications. Machine and edge are equivalent to the machine and edge adapters in the structures discussed on the last slide. The middleware and the cloud-based application is a permutation of the data historian, analytics module, and clients of the last slide. Coming to the machine layer, it consists of the machine tool, the data acquisition system, as well as all the sensors which are integrated onto the machine in order to collect the data. Once the data is collected by the data acquisition systems, then it is transferred to the next layer, that is the edge layer. The edge layer consists of different ways in which the data can be processed once it has been collected by the DAQs. Once the desired pre-processing is completed, it is then forwarded to the next layer, that is the middleware. The middleware involves functionalities such as the proper storage of data in the cloud or edge, depending on the requirements. Similarly, it can secure and keep the data backed up at all times and can form a link or a bridge between the server and the clients. Followed by this, finally, we have the cloud-based applications, which host the marketplace for several different applications. The idea here is that it can act as a collaboration hub wherein different users can deploy their applications for open source use In our implementation, this layer consists of applications which are derived from various metrics such as the productivity matrix or the quality matrix, as well as a real-time user interface in form of a web-based dashboard which can be accessed from anywhere. Going down a depth below and talking about various entities which are present within these blocks, we have several alternatives in our SM implementation, such as the alternative of the using LabVIEW or the Python-based processing at the edge, or be it the use of OSIPI system or the Sesame's SMIP, which is the Smart Manufacturing Innovation Platform by Clean Energy Smart Manufacturing Innovative Institute, which is a funded institute by DOE. Followed by that, the green arrows on the screen here are the routes which we have already successfully implemented. And the red arrows here are something which still lacks certain research, and we are still working on including them in our architecture. Finally, the thicker green arrows here are the route which we followed in our paper, and these will form the major topic of the presentation further on. Followed by that, let me quickly summarize the implementation that we have at Texas A&M. We have an optimic hybrid machine which, as the name suggests, is capable of both additive and subtractive processes. Here are some of the capabilities on the machine which goes from milling to CMM to grinding to 3D printing. Coming to the sensors, as of now, we collect 13 different data streams based on a combination of different sensors. Here are some of them, which includes the accelerometer, a high-speed camera capture, which is essential for looking at slowed down version of the process itself, a temperature sensor by Stratonix, which is used for capturing the melt pool during the additive cycles. Followed by that, these are some of the synchronized streams that we have at Texas A&M, which were captured during a DED-based additive process. Going in order, we have a smartphone-based video capture of the entire experiment, followed by a high-speed camera-based capture, which can go up to 900,000 frames per second, giving us the ability to look closely at the melt pool and even the interactions of the powder particles as they come in contact with the pool. We also have a thermal capture of the melt pool, which can capture several different parameters, such as the minimum temperatures, the peak temperatures, and the video frames themselves. We use OPC UV to keep a track of any movement changes in the tool or the printing head throughout the process. Finally, we have several different sensors such as the thin film force sensor, the accelerometer, and the acoustic emission sensors by which we capture certain vibration phenomena and then later on pre-process them in order to align into the spectral domain. Similarly, this is a version of the previous slide, but in case of a milling operation on the hybrid machine, and we are trying to capture several different synchronized frames at the same time. It is important to talk about the considerations that arise in such an SM-based architecture. We have already talked about some of them in the previous two slides, but most of it had to do with the edge part. Coming to the next part, we are going to talk about more considerations that align with the cloud part. At the edge, we have already discussed that synchronization of various different sensor streams is an essential step. What's the point of having an edge cloud-based implementation setup if my data is going to be transmitted with delays, and that's obviously going to overshadow the process which I'm trying to track? As of now, based on timestamp analysis, we have been able to cut down and synchronize all the data streams to a precision of a couple of milliseconds. Coming to the cloud level, we are always going to run into the trade-off decision of how accurate we need to be as compared to the latency. The data integrity needs to be maintained and the data needs to be transferred in a loss-free and timely manner. Similarly, the security of the data is also an essential step which needs to be integrated. Coming to the results which we obtained by integrating our implementation with Sesame's SMIP, we were uploading and downloading 240 data samples for testing the same, and SMIP did not drop even a single sample of experiment, preserving the data integrity throughout the experiment. Minor differences were observed with respect to timestamps and floating points, but the values were pretty low, and most of it was associated with rounding off to a precision of microsecond at the network. The floating point differences like a combination of multiple Gaussian distributions which were aligned to different causes of noise. The testing was also based on different transmission modes, which included the serial and the asynchronous transmission of 1000 samples per chunk and 8000 samples per chunk. In case of serial transmissions, the bigger chunk sizes competed as twice as the smaller ones. However, in case of the asynchronous transmission, the smaller chunk sizes were able to perform faster and the trend reversed. Given that we have found that 1000 samples per chunk was the fastest way to upload and download, we tested it out on different sizes of the samples, and we observed that both the upload as well as the download trends were linear. At larger data sizes, the downloads are consistently faster than the uploads. This is because the data lookups are much faster than insertions. At best, we were able to achieve a 23,000 kHz rate to and fro loss-free transmission from SMIP. At the client end, we'll have a similar dashboard running which will keep track of different productivity matrices, including different sorts of times. Similarly, it will also keep track of a quality matrix and keep track of anomalous parts. And finally, we'll also have different application matrices embedded into the dashboard, such as a surface roughness estimator. To conclude, let me go over the key takeaways of the paper. Firstly, we are able to successfully implement and test our SM platform as it integrates with Sesame's SMIP. With a completely open source route, we were able to achieve a sampling rate of 23 kHz, which is expected to scale and further with network and hardware upgrades. Our implementation houses the ability to provide custom solutions to our clients so they can set up their desired data pipelines and achieve an efficient implementation on their end. Finally, we were able to enable advanced process monitoring of the manufacturing operations, which is not only based on multiple sensors but also several visual and videographic captures. Moreover, our implementation harnesses the capability both at the edge and at the cloud. To conclude my presentation, I would like to acknowledge the support by Texas A&M University's X grant, the Rockwell International Professorship. I would also like to thank Sesame, especially Jonathan Weiss, for his valuable feedback throughout the project. Last but not the least, I would also like to thank my advisor and my lab mates for their constant support during the collection of the data or be the day-to-day activities during the time of this project. Thank you.